Okay, hello everyone. Welcome to this webinar series on advanced mobility by the IEEE Vehicular Technology Society. Um, so here is the acknowledgement that the organizers asked me to put. Thanks a lot to VTS for inviting me to give this talk on some of my recent work on joint radar communications, which is a very actively researched topics these days across not just IEEE VTS, but some other 14 different IEEE societies actually. And in particular, I'm going to focus on the distributed joint radar communications. Uh, uh, Here is a brief description of what I do. So I've been a senior fellow at ARL here in Adelphi, Maryland, very close to Washington, D.C. I'm also a research fellow at the University of Luxembourg. I also serve as technical advisor of two very promising startups. The first one is Hertzwell, which is based in Singapore. It is Asia's first automotive radar startup. And Aura Intelligent Systems, which is a 5G imaging radar startup in Boston. And I interact with various IEEE societies, VTS, AESS, ComSoc, either in my editorial capacities or a member of different working groups. My primary research interest is radar, and I investigate its connections with signal processing, electromagnetics, communications, and remote sensing. I would like to acknowledge a number of my collaborators whose work will be featured in this talk. So from ARL, Dr. Brian Sedler, from Luxembourg, Bhamani Shankar, Bjorn Otterston, Ahmed Elbid, from Texas, Dallas, Mohammed Saqib and his student Giavi, from the Industrial University of Santander in Colombia, Henry Arguello, and his excellent students, Edwin, Roman, and Jonathan. I would like to thank DEVCOM ARL as well as the National Academies of Sciences, Engineering, and Medicine for funding some of the research that will be featured in this presentation. So in my presentation, I like to put some snippets from my favorite science fiction TV shows or movies where they are talking about radar or wireless communications. In particular, the snippet that you see here is very relevant to the talk today. This is from a very popular Apple TV Plus show For All Mankind, which is about a bunch of NASA scientists, and it is based in 1960s. And in this scene, they are talking about interference from solar flare on ground-based communications network. And in fact, if you scan the literature and go to 1960s or late 1950s, there used to be an IEEE journal, IEEE Transactions on Radio Frequency Interference, where a lot of papers were published on interference from solar flares on the broadcast spectrum. So the problem used to be that severe that even a natural interference like solar flare could just jam the whole communications network on Earth. So that is an example of natural interference. Today, I'm focused on the problems that arise from man-made interference from one emitter to another. So, for example, from radar emissions to communications or vice versa, and so on. So let's look into the motivation for joint radar communications these days. So the interference from different emitters to each other, as you can see, is not a new problem. It has been around for a while. Very early papers you can find to 1960s, where if there is an interference from one emitter to another, people have proposed, can we use a joint hardware or can we use a common waveform so that which can perform functionality of both radar as well as communications or other services as well. But the problem, and there were some other scattered papers in 70s from NASA, but this problem was really noticed in 1980s when in the lower frequency radars like L-band radars or UHF, VHF radars, where foliage penetration radar operates and it has very wide spectrum. And in 1980s, that radar started encountering interference from TV and broadcast stations. and that led to the redesign in the receivers that can we notch out some frequencies in the receiver so that this interference could be done away with. Because the spectrum was so wide, even if you notch out the frequency in that particular radar, it doesn't lead to a lot of signal distortion. So there was some work on at least interference mitigation at that time. But it is really in the last 10 years that there has been a very frantic activity in this area of joint radar communications or looking into interference from one another. So the reason for the primary drivers for this, I'm going to discuss now. One is from the communications industry and another one is from the radar segment. So if you look into the trends in wireless communications industry, as a graphic here that I've taken from some industry sources shows that there are now billions of devices that are already connected with each other. So in 2020, about 50 billion devices were connected, and it is expected that this number would have risen dramatically by now. The data and cloud traffic has increased manifold. And there is also a demand for very high quality wireless services now, gaming, high definition TV transmission, and so on. And if you want to connect so many devices and also want to provide very high quality wireless services, we need to have high data rates. And the question is, how can we meet this ever increasing demand of high data rates in the current scenario? For that, we only need to turn to Shannon's formula as a guide. The famous capacity formula, which says the capacity C, which determines the data rate, is controlled by these three factors. The first is N, which is the number of non-interfering or orthogonal resources. For example, number of antennas could be one such resource. So if you increase the number of antennas at transmitter and receiver, that can help in increasing C. This is the concept of MIMO communications. Then we have bandwidth W, that will come to that in a bit. And signal to interference plus noise ratio, but you'll have to increase SINR a lot to see any appreciable increase in C because they have a logarithmic relationship. So we are stuck with playing with N and W. So, and I, like already mentioned, you can increase the number of antennas. As far as W is concerned, then the wider the W, it is better because there is a linear dependence between capacity and W. But electromagnetic spectrum is a scarce natural resource. We cannot increase W indefinitely. So in that case, there are, and moreover, even if bandwidth is available, not all the bandwidth could be useful because there are regions where the attenuation is high in the spectrum and so on. Further, national and international regulatory bodies like FCC and ITU, they have already allocated spectrum in the lower frequency region. So that region, the sub 6 gigahertz region, as you see in this graphic, is already very crowded for the traditional cellular communications. So people are moving towards the higher spectrum range, for example, millimeter wave or sub-terahertz as shown here, where very wide contiguous bandwidth is available, which can actually support the kind of data rates that we just saw in the previous slide. And it turns out that this contest of spectrum is also not new, as some headlines here show that among the wireless service providers, they have been asking FCC to allocate more and more spectrum. So right from 1980s to even until very recently, you can see this kind of pressure from the wireless communications wireless service providers has been consistent in asking for more spectrum. So wireless communication industry needs wider bandwidth to support all these different services and high data rates and to connect many users. Now, let's look at the second driver of this wide bandwidth phenomenon and which has led to the joint radar communications paradigms. So the second motivator is from the automotive radar industry, where modern autonomous vehicles, they are driven by several sensors. They are equipped with several sensors, as you can see from this graphic here: GPS, LiDAR, cameras, ultrasonics, radar. And the goal of these sensors is not just to guide the vehicle in a crowded traffic environment, but also to monitor the general health of the car. For example, we have sensors for tire pressure and similar other functionalities, as well as to monitor the physiological behavior of the drivers. So we have in-cabin sensors to monitor the heart rate, respiratory rate, etc. of drivers and other passengers. But if we focus just on autonomy, then chiefly three sensors are very common. First is a very high resolution camera, provides a good visual, has semantic information. But when the visibility conditions are poor, for example, in night or in adverse weather, then it doesn't give very good performance. And it also does not measure Doppler velocity directly. It only infers it after looking at the changes between different frames. Then we have LiDAR, which is very high resolution because it operates in the optical range where wider bandwidth is available. So people who may be familiar with the LiDAR or radar signal processing may recall that wider the bandwidth, the transmit signal bandwidth, higher is the resolution of that device, which means better is the capability to distinguish two very closely spaced targets. So LiDAR operates in optical range where extremely wide bandwidth is available. Its resolution is very high, very highly accurate, but then it is expensive, and in automotive industry it does not really meet the cost that is set as a golden standard by automotive industry. Like these sensors should be $100 per batch production, as per one of the General Motors white paper released a few years ago. So LiDAR just does not mean that, it is very expensive. So we come to radar in that case. So radar is all weather, because I mean, whether it is day or night, or even at least for the distance that automotive radar is supposed to observe, even if there is rain in between, it doesn't affect its performance a lot. So it is robust to these conditions. It measures Doppler velocity directly because it operates on Doppler principle. It's low cost. Now, the question is that, okay, it's not as good as LiDAR in terms of resolution, but that's why the efforts are underway that if we can provide more bandwidth to the radar, then it can provide near visual resolution, just like LiDAR. And this is usually done by operating at millimeter wave or upper millimeter wave or low terahertz bands for automotive radars. Moreover, most of these modern vehicles, they have become increasingly software managed. Several functions are now controlled by the CPUs equipped on cars, and they're also supposed to be connected to infrastructure, to each other, to satellite, and so on. And because of these functionalities, they generate enormous amount of data that the current sub-6 gigahertz wireless technologies like DSRC and CB2X, they are unable to handle. So if there is a huge amount of data and we want to handle that, as we know from wireless comms trends, these cars, they need to have very wide bandwidth in that case for communication as well, right? So the autonomous vehicles, they need wider bandwidth to sense accurately and to stay connected. But bandwidth is, or spectrum is very limited, as we know. As you can see from the table here, pretty much every IEEE radar band these days has some coexisting communication service. And as I mentioned earlier, the problem of interference from radar to communications in 1980s, like we discussed, was in VHF, UHF band, open radar and TV broadcast stations. But now this problem is becoming very common across other bands because of new applications, new radar applications that are coming in, as well as with the advent of better cellular communications services and demands. And the problem is not just localized to radar devices. Last year, there was news that, and it was a very highly public battle between FAA and US Airlines, where the FAA asked US Airlines to actually stop operating their 5G services around airport because their C-band frequency was interfering with the radio altimeters that are used by FAA. So they had asked Verizon to stop the 5G services at that time. And then last year, US Airlines, they started installing the C-band filters to notch out the those 5G frequencies used by Verizon. Um, Radio astronomers are complaining about interference from satellites. It's interfering with clean sky observations. Meteorologists are concerned about interference from wireless technology because sometimes that interference shows up as a storm on weather radars. So this problem has become pervasive now, and several other government agencies, they are now looking into. They have been looking into solutions to develop spectrum sharing systems where the same hardware can do multiple functionalities, or there at least there's a common waveform or coordination between different emitters, how they transmit, at what time they transmit, or just find out mitigation technologies for interference. So DARPA about 10 years ago had this program SSPARC, which was about developing spectrum sharing solutions between S-band radar and S-band communications. And later on, NSF started expanding it to all other bands through various programs, some of which I have listed here. So this has become a very popular topic to investigate nowadays. Now, if you look into some of the design solutions for this problem, so what kind of spectrum sharing solutions are possible? So in joint radar communications, and some people also prefer to call it integrated sensing and communications, or ISAC. This is a communication society term, but now is now widely adopted. Or sometimes you can also hear term like dual function radar communications and so on. So if you want to classify different solutions that have been developed in past few years, very broadly based on whether the transmitter and receiver is shared or not shared between radar and communications, we can have these four classifications. So if none of the hardware is shared and both radar and communications are accessing the spectrum independently, in that case, we have the spectral coexistence solution. So here, obviously, there will be interference because there is no coordination. So most of the novelty or research here is directed towards developing better receiver processing algorithm to mitigate the interference or to extract the relevant information for radar and communications. And if any one of the hardware is shared, in that case, we call those as spectral co-design solutions. So for example, the very general one will be this D, where I've shown a vehicular scenario where there is this red car, which is the transmitter, the common transmitter for both radar and communications. It's transmitting a common waveform, which has which is a radar waveform, but with communication messages embedded in it. It interacts with the target or this blue car, and then it is reflected back and intercepted by a common receiver, which is this gray car. And the goal of the signal processing at this receiver is to extract the parameters of this blue car, for example, its location, Doppler velocity, and so on, and also to decode the message that was sent by the red car. So common transmitter, common receiver, common waveform in this case. So this is a true spectral co-design approach. Obviously, there are these are very broad classification, but there has been a lot of research in this area and still continuing. So you can classify the solutions further based on the type of waveforms they use, what kind of channel access, based on the location, if there are multiple transmitter receiver or just a few. So you can have co-located, bistatic, widely distributed, and so on. Depending on the functionality, whether you're focusing more on optimizing radar, then it becomes radar centric. Otherwise, it could be comm centric, or if both are almost equally optimized, then we call it joint radar comms or DFRC kind of solutions. And then there are other specialized variations like joint MIMO radar, MIMO comms, MRMC, in-band full duplex, or using intelligent services. Depending on which band you're operating in, you can have different solutions. So there's a lot of work going on. And as I mentioned earlier, about 15 IEEE societies nowadays, they have published some work related to ISAC. So if you work in this field, it has become very cross-disciplinary these days. So that was the motivation and introduction of the whole landscape of ISAC. Now let's look into some of the examples of these solutions that I had mentioned earlier. For example, spectral co-design, then opportunistic Isaac, and if time permits, we'll look into a very interesting problem within spectral coexistence. So let me start with an example, three examples in spectral co-design. And the first one is that diagram that we saw on automotive JRC, which was this bistatic case. And we are considering bistatic. So bistatic means that the transmitter and receiver, they are not at the same place. And it is used for radar in general. You can have a monostatic case where the transmitter receiver of the radar are at the same vehicle, like this truck, but the communication receivers, they could be on other cars. So in a traffic scenario, vehicular scenario, it makes more sense to look into bistatic or multistatic because usually the signals are reflected back and it could be intercepted by other cars because it's a crowded traffic environment. And sometimes there may not be a line of sight situation between the transmitter and receiver, which is advantageous because then the receiver can also sense the transmitter can help in detection of the targets which are not in line of sight for, let's say, the receiver, right? So and moreover, in this case, compared to the monostatic case where the coverage is almost this circular because transmit receive are on the same car, in case of bistatic, because the transmitter and receiver are separate, the coverage in one direction could be elliptical and could be more than the monostatic case. So this analyzing the whole situation through bistatic or multistatic can also lead to range extension. That's why we look into bistatic case the most. Now, let's look into some of the problems that we encounter in this case. So the first is the selection of waveform. Because radar and communications, they perform completely different tasks. Uh, it is difficult to choose a waveform that can do both radar and communications. Typically, either you can design a customized waveform, as we'll see in another example in a bit, or you can use some existing waveforms from radar and communications, and then see how their performance is in the joint radar communications mode. So for example, here we chose two waveforms. One is the phase modulated continuous wave, which is nowadays becoming very popular for automotive radars as an alternative to FMCW, and it has a very sharp thumbtack ambiguity function, which means zero side lobes. You can do the detection of closely spaced targets even better. And then OFDMA, which is very popular in the communications. It's like OFDM, but it can differentiate users in both time and frequency. It has a good performance as far as the Doppler is concerned. So we wanted to see if these properties of PMCW and OFDMA, do they hold when we look into their ambiguity functions in the joint radar communications mode. And after some analysis, when you derive these functions and then plot them, it turns out PMCW in the JRC mode, all of these waveforms in their JRC mode, they do inherit some of the properties of their parent waveform. So PMCW JRC has a good performance in the range domain, and OFDMA JRC has good performance in the Doppler domain. So here is an example of a full system, the joint transmitter, joint receiver system. So yes, I mean, as you can see here, the receiver is more or less the same for both PMCW JRC and OFDMA JRC. But the transmitters are slightly different just because the way these two signals are generated. However, if you are transmitting continuously just PMCW, both the joint radar communication signal all the time, then there is a problem of differentiating the radar from communications at the receiver. Yeah, because then we have all these coupling related problems. It becomes very difficult to distinguish the two at the receiver. So in that case, to address this, we do some kind of multiplexing, both for PMCW and OFDMA. So what that means is that for some of the pulses or some of the subcarriers, for example, in OFDMA, you transmit just a radar-only waveform and then transmit radar and communications together for the rest of the pulses. You can alternate between these. And if you do this, then at the receiver, it helps in decoupling some of the parameters. So for example, in PMCW multiplexing, we are doing this in time domain. So radar only signal, then radar communication signal, then radar only, and so on. And here in OFDMA, we reserve some subcarriers for radar only and some for radar communications. Now, exactly how much should be for radar, how much should be for radar communications, it is a trade-off depending on what kind of performance you want. Shown here are a few results. This red one is a theoretical curve, which is what we would like to achieve. And here we are assuming that we are transmitting radar communications for all the pulses and all subcarriers, and we are able to successfully decouple the communications from radar at the receiver. So this is just theoretical, but in practice, that won't be the case, because in practice, this decoupling is usually imperfect. So we show here the blue one. Blue curve says that the decoupling is the removal of communication symbols, for example, is imperfect, but we are using radar communications for all the subcarriers in this case. So you can see that with SNR, increase the root mean square error for the parameter estimate, it comes down for this blue curve, but it is very high for low SNR. So, but however, at low SNR, if you do this multiplexing, like half subcarriers for radar, half subcarriers for joint radar communications, that then at low SNR, you can actually improve the estimate through multiplexing. So you don't need multiplexing when the SNR is very high, then the performance will be good despite the imperfect decoupling. But at low SNR, multiplexing can really help. Now, this was one example. Now, let's look at another example that is of the distributed case. So far, we are considering co-located cases, but when there are multiple transmitters, multiple receivers, then the problem becomes very difficult. So the complexity is high because of so many nodes. Then how to synchronize the transmission and the reception of all those nodes could also be an issue. In case of radar, we usually characterize the performance for distributed radars in statistical way. For example, we don't have a deterministic definition of the ambiguity function that I had just mentioned earlier for the PMCW. Here we have a probabilistic definition. We need algorithms that have low latency, that are faster, because if you're operating in a network, that becomes an issue, and so on. And then there are other considerations. For example, duplexing could be a consideration. So now with the 3GPP new release, duplexing is a part of this. So here transmitting, receiving at the same time, and same frequency means a lot of self-interference, so that you have to take care of. There may or may not be a fusion center, and that changes the processing algorithms. And finally, the architectures are very different for distributed ISAT. You can have each radar could be a different type of radar. So it doesn't have to be a homogeneous node architecture, but could be heterogeneous. And even intelligent surfaces are sometimes thrown into these architectures, which make the problem very complicated. So we wanted to look into one example here. So distributed radar is also called statistical radar, because the target in a distributed radar network, its target cross-section doesn't appear identical to any of the TX-RX pair you choose. It can appear differently. And this spatial diversity could sometimes be useful. For example, detection of stealth target could be done that way, because if you're using just one radar, then the stealth target has the ability to scatter the incoming signal in another direction. But if you spread out your network, then even if this target scatters it in another direction, you can catch that signal through a network of radars. So the way we model this target RCS is using the random variable for the channel, and that's why it is also called statistical minor radar. So we considered this study where we have a statistical MIMO radar, and we also have several uplink users, downlink users, and a base station. And then we wanted to do a customized design for a waveform filter and precoders for such a system. Moreover, here we don't want to treat interference as nuisance all the time. For example, if a communication signal interacts with the target and comes back to the radar, then it still has useful information about the target. And if we could use it in cooperation, then we show that you can increase the detection performance manifold. So here's a system model for this kind of system. So I'll just summarize it, although it looks very complicated. So we are transmitting the MIMO radar, all of its transmitters, they transmit this periodic pulse train at regular intervals that we call pulse repetition intervals. Similarly, BS transmitter and uplink users, they are also transmitting their communication frames. So the assumption we make here is that there are KPRIs and K frames in our observation window, but they need not be synchronized. The radar need not transmit at the same time as the base station and uplink users, because they may not share the same clock. So there could be some gap also, but that could be taken care of in the model. And in each of these transmitters, so if we look into the radar transmit signal, we are going to design the radar code matrix. So this radar code, that is what we want to design, what should be the optimal radar waveform. For the uplink user and base station transmitter, we want to design their uplink and downlink precoders, that is these matrices P. The receive signal, if we look into, that is somewhat interesting. So we have three receivers here, right? We have the receiver at the base station, which is receiving the which is receiving the uplink signal. So here, this is the first equation. Second equation is the receive signal at all downlink users. So at each jth downlink user, you will get an equation like this. And then the signal at the radar receiver. Now, in all the cases, you have noise. So we have just pointed it out here in that circle. Let's look at the first equation. So here, the first variable here, that is the signal that we want to decode. That is the ith user, uplink user signal. Then the second term is the multi-user interference. Then we have the interference from radar, and we have the full duplex self-interference that I mentioned earlier. So we treat all these three terms as interference, and then the fourth term is noise. Only the first term is useful, that is the uplink user signal. Similarly, at the downlink receiver, you have the jth downlink receiver user equipment signal. And then there is multi-user interference. There is also signal that is coming from uplink, that is an interference too, from radar, and so on. So a lot of interferences here. At the radar, we have clutter, we have uplink signal, downlink signal, those are interferences, but we also have communication signal that interacts with the target and then comes to the radar. So the radar signal is the first term, but the communication signal coming from target, that could also be useful. So we show later that if you combine both of them for estimation of target, that increases probability of detection. And for all these other interference, we need to design better filters. So now our problem was that design waveform, design better filters and precoders. So you can read details in our paper. It's a very long paper. We do this non-convex optimization. It is an iterative method, and eventually we get those optimal filters. But I wanted to share the result here, and the result here is as follows. So we are looking at the probability of detection here. And when we don't use downlink reflected signal at the radar and just focus on extracting target information from the radar signal in the presence of all this interference, then the performance is this dotted line, which is really the worst. But when we combine the downlink reflected signal and then use the strength of using this common signal, in that case, the probability of detection gets bumped up significantly, as you can see with the this solid black line here. The final example of this spectral co-design is to use machine learning. So as I mentioned earlier, that a lot of these systems, they have high dimensionalities, could have multiple nodes. So we need algorithms that are quick, that have low latency and so on. And machine learning really helps with this. So let's look into one of the examples where we used machine learning in a joint radar communications problem. So machine learning, we don't use this for automating the whole system. We focus on some narrow problems where we want an excellent performance that conventional algorithms are unable to give. Now, of course, machine learning requires some of the algorithms that we are using on architectures. It requires labeling of the training data, and that could be very tedious. But then with reasonable effort, we can do labeling of training data. Of course, there are other methods like reinforcement learning or semi-supervised learning, where labeling effort is not that high or just negligible. But with label data, you definitely get very state-of-the-art results. So we use machine learning for some narrow problems rather than automating the whole ISEC issue. And hybrid beamforming is one such case, especially at higher frequencies like terahertz, where the dimensionality of the problem is very high. That machine learning can be very beneficial in that case. If we look into just radar, what kind of problems learning helps there? So typically for target classification, analysis of microdoppler signatures, or even waveform classification, these are standard applications of machine learning in radar. If you look into communications, then the standard applications are signal detection, channel estimation, antenna selection, beamforming, and user localization. So localization is a common application in both radar and communications where learning could be used, and similarly beamforming or antenna selection. These are some common applications. So we would now look into a beamforming problem, but for terahertz. And the challenge here is that at terahertz, at that frequency, attenuation is very high. And to compensate these losses because of attenuation, we use very large arrays. And when you're using these large arrays in order to compute the beamformers, especially hybrid beamformers at such a high dimension, that could be very tedious and could be computationally expensive too. So that's why we would like to use deep learning. I show here an example of some of the array architectures we use because it is hybrid beamforming. You would recall that we cannot have dedicated RF chain for each antenna because it would be very expensive when you're using hundreds of antennas at terahertz. So usually we do beamforming at subarray level, like group of subarrays where we don't use a phase shifter for each antenna. We don't have a dedicated RF chain for each antenna, but a group or subarrays of them just to bring down the cost. And then the beamforming is done both in digital as well as analog domain. That's why we call it hybrid beamforming. Here is outline of the optimization problem. As you can see, it's very complicated. The joint radar communications, hybrid beamforming, it's a non-convex problem. There are several non-convex constraints also on the beamformers. And typically, we use this factor eta here, which weights the radar and communications performance, which performance you want more. So if you take it 0 or 1, you can weight radar and communications more or less in that way. So I'll show an example of that eta in a bit, but how we are doing beamforming here. So we use two convolutional neural networks. The first one takes the array output, the received signal, its covariance matrix as input, and then it gives out the radar target directions. Once we have the radar beamformer, which is FR, we take that and the channel estimate edge. You can use a learning network also to estimate the channel. So you combine, here we are not using it, but you can do that. You combine FR and H as input and give it to another convolutional network that gives you out the hybrid beamformer for communications. This is much faster. Of course, to generate the training data, you will have to solve these problems the conventional way, which can take a lot of time, but that is a one-time upfront cost. After the network is trained, then you can get these outputs very quickly. So shown here is an example. So as I was saying that if eta is 0, we are only weighting the radar performance. So that this dotted line is the communications user. The solid red lines are the radar target. So as you can see, communication user, we don't have any beamforming when eta is 0. Similarly, when eta is equal to 1, then the radar performance is not that good, but the communications user, the beamforming takes place in that direction. And when it is 0.5, then you can get reasonable beamforming in direction of both comms user as well as radar. The next type of category in these solutions is the opportunistic ISAC, where we already have a communication protocol or communication infrastructure, but we want to use it for data. So an example of this is 802.11ad based Wi-Fi protocol, which is used at 60 gigahertz, and it has been suggested for vehicular communications a lot. So a few years ago, people started looking into, can we use this for radar as well? And the reason for that was the structure of 802.11ad preamble. Because if you look into that preamble structure, then it has what we call as GOLI sequences. These are signals which are equal in length, usually in the power of 2, where the power is greater than or equal to 5. So they occur in lengths of 32, 64, 128, and so on. And they are embedded in the preamble of 802.11ad. Okay, so far so good. But what is their nice property that enables this radar sensing? The property is when you autocorrelate each one of the sequence with itself. So let's assume that the sequence has these two sequences, GA and GB. I autocorrelate GA with itself, GB with itself, and when I sum them up, I get a delta function. This is like that ambiguity function property that I was mentioning earlier, where I was saying it has low side lobes for PMCW. But here they are not just low, they are zero side lobes. So this is what we call as perfect autocorrelation property. If we use such a signal for radar sensing, then it can distinguish two very closely spaced targets very well because there are no side lobes at all. That's why people wanted to use this for radar sensing as well. I mean, we are transmitting a signal anyway. If it comes back to us, let's extract the preamble and then look at what information we can get from the target. So this was all good. This work was done earlier around 2017 by the researchers, but there is a problem. This perfect autocorrelation property is only valid for stationary targets. When the target is moving, then it actually adds this additional phase here to the second autocorrelation, and then you don't get that perfect autocorrelation. But in our traffic scenario, in a vehicular scenario, targets are always moving. So we needed to make some changes to this design in order to make it compatible to moving targets. And for that, the way we proceeded is as follows. So there is something called Pruhet-Howe-Moore sequence or PTM sequence proposed in 2008. What it says is that don't transmit just GA, GB, GA, GB. Rather than now you transmit instead of that one pair, transmit that pair again, but reverse the sequence, GA, GB, GB, GA. And then once you take these re-sequenced GOLI pairs, and then sum their autocorrelations up, then through Taylor series expansion, you can show that you can get Doppler resilient region for some moderate Doppler velocities. So even though it is not completely side lobe free at all Dopplers, because if you want it at more Dopplers, you have to actually average more of these GOLI sequences. So depending on what kind of trade-off you want to do, you can at least achieve a Doppler resilient region for some of the moderate Doppler velocities. So we decided to do this, and then we did some experiments using this PyBullet software, which is a physics modeling software. You can take scattering models, electromagnetic scattering models of different vehicular targets, like for car, bicycle, we model it using cylinders, pedestrian using ellipsoids, and you can provide a trajectory in that software where you can look into the signature that you can get. So here, this is the car trajectory, this is the pedestrian's trajectory here, this arrow, and this is the radar location. And then we transmitted the standard GOLI and this Doppler resilient GOLI case in both cases. And then we wanted to look into what kind of signatures we are getting. So this middle panel is the standard GOLI, and the lower panel, bottom panel is the modified GOLI. As you can see in the bottom panel, we don't get any this side lobe kind of interference. It's very clean signal, and we can distinguish very fine returns like individual wheel returns, or for a pedestrian, it's torso returns, or human legs and hands. All those could be seen individually in this case, which helps in better target recognition. This can also be extended to drone-borne radars, where again in PyBullet you can input the surface texture models and then do the similar analysis for standard GoLi as well as this modified GoLi. The final piece of this puzzle, we have a few minutes, so I would just give this final example, which is from spectral coexistence, dual blind deconvolution. This is the work that we have been doing for past 3 years now. And the problem is as follows. So in radar, we transmit the signal, but we don't know the channel. And at the receiver, the received signal is a convolution of the transmit signal and the channel. And our interest is in determining the channel, assuming that the transmit signal is unknown. But in certain situations, for example, in passive radar, where someone else is transmitting the signal, we don't know the signal either in that case. So when, at the convolution that you have at the received signal, both convolvents are unknown, the transmit signal as well as the channel. Now, in communications, that situation can arise in a vehicular environment. So in communication, the conventional situation is reverse. We don't know the transmit signal, but channel we estimate a priori. And then at the received signal, which is again a convolution of the transmit signal and the channel, the goal is to just estimate the transmit signal. But in a vehicular scenario or other dynamic communication scenarios, the channel becomes outdated very quickly. So there can be a situation where you don't have a good channel update. So the channel is unknown as well as the transmit signal is unknown. Now, consider the coexistence situation where these two kind of signals, where both transmit signal and channels are unknown, they are superimposed or overlaid on each other at the receiver. That can happen in a coexistence scenario. So this is what we call as dual blind deconvolution problem. So here I've written this signal at the receiver, where it is the first convolutions from radar, second convolutions from communications. You can have n-tuple blind deconvolution also, where you have multiple emitters which are transmitting. That can also be addressed as we show in our paper, but here I'm just showing the dual blind deconvolution case. So it is called dual blind deconvolution, dual because there are two convolutions, and it is blind because none of the convolvents are known. So how to solve this problem? How to extract the radar target information and transmit signal, the communication message in this case? So it's an ill-posed problem. So the way we address this is, first we assume certain structure. So transmit signal for radar, we assume it's a pulse Doppler radar transmitting a pulse stream. And for communications, it's an OFDM signal. And the channel in both cases, we assume they are delay Doppler channel. Like L targets here, Q paths. So we have their respective delay and Doppler. Now you discretize the signal and substitute all of these expressions in the first equation. After some tedious algebra, we get this last equation that is shown here, which has a lot of unknown variables that we want to estimate, primarily related with the channel of the two systems and then their unknown transmit signals. Still difficult to solve. So the way we proceed is as follows. We assume that the channels are sparse. As you saw, they were indeed sparse. They were delay Doppler channels. Then we assume what we call as a lifting trick, that the transmit signals, they lie in some low dimensional subspace. And after all of that, and a lot of tedious algebra that you can find in our JSAIT paper that I've listed here, it was published this year in Journal of Selected Areas in Information Theory. The whole problem could be formulated as an atomic norm minimization problem, where we are trying to find out these matrices ZR and ZC, which contain all these unknowns for radar and communications respectively, by minimizing the sum of their atomic norms subject to these equality constraint, which is essentially the observations. What is atomic norm? It's a generalization of L1 norm. So if you recall, in sparse reconstruction, we solved the L1 norm minimization. Now, if you generalize that to any kind of basis, where the basis could be rank 1 matrices or DFT basis and so on, here in this case, it turns out it's a rank 1 matrices, then you can do the same sparse reconstruction, but by solving the atomic norm minimization. minimization. The difference here compared to the conventional atomic norm minimization cases is that we are first of all doing minimization of some of atomic norms. And even each one of these atomic norms, they are multivariable, they are high dimensional because they are unknowns in both delay and Doppler. So it's a little bit more complicated. The way we typically solve this is by converting that primal optimization problem into its dual optimization, and then using properties from positive trigonometric polynomials, you can actually find out the semi-definite program for that problem that I showed earlier. So I skipped those details, but I show the result here, where we are plotting that dual polynomial for both radar and communications in the delay Doppler plane. And the guarantee, the theoretical guarantee that we have here is that wherever that the maximum modulus of that polynomial achieves unity, that is the location of your target or delay Doppler in the case of communication. So you can recover them accurately. There are many generalizations that we have done for this problem in presence of noise, multiple emitters, lack of synchronization, and this problem beautifully extends to all those scenarios. You can see more details in our paper. So obviously this this talk is not sufficient to summarize so much that is happening in Isaac literature these days and in Isaac research. So I've given a few other examples that may be of your interest, for example, using sensor fusion techniques or using intelligent surfaces in joint radar communications. We also have work on the security issues related to DFRC and other architectures. I provided the references here. Please feel free to go through those references. And I would like to close in by plugging in my book by IEEE Press on signal processing for joint radar communications, where you can find a lot of details related to everything that we have talked so far in this book. There are many interesting chapters. If you're interested in following my other talks and tutorials, please follow me on LinkedIn, where I post regular updates related to Isaac research. So with this, I would like to thank you, and I'm happy to take any questions you guys might have. So I see one question by Kamesh. Yeah, hello, Kamesh. It says that, what is the application that you're currently investigating? Ground vehicles or aircraft system? The RC problem becomes more challenging when applied to drone communications because TX and indeed, yes. So far we have looked into mostly ground vehicles and of course, even drone to drone, you're saying TX, RX are moving, but in ground vehicles also they are moving. Synchronization of the signals becomes a big issue in this case. So we haven't investigated synchronization that much. That means I personally, but there are other researchers who have looked into synchronization issues for bistatic or multi-static cases. What kind of protocols should be used to do this? Drone to drone, you can think of it as, for example, as far as radar is concerned, this is not something new because airborne radars have been there which detect moving targets. So the literature has been available there. But in a joint radar communications, how to do that, I think that's probably somewhat new. People have looked into different aspects of this problem, but not everything in a single paper. That I don't recall.
Yeah, thank you, Vijay, for a wonderful presentation. Actually, I attended your other seminar on signal processing webinar as well. There's a lot of information, in fact, and obviously the book that you are showing will give us more some details and in-depth information, I believe. Thank you. Thank you for that presentation.
Okay, any other questions? And as I said, all of you are free. Please feel free to follow me on LinkedIn or connect on LinkedIn. And you can also send your questions later via email. Okay, thank you, Srijit.
Yeah. Thank you, Vijay Kumar.